Hello everyone, and thank you for attending this talk. My name is Mihail Rumensev, and I will be presenting my research on transformer-based multimodal framework for music similarity and recommendation. This study aims to improve how music is analyzed and recommended by integrating multiple data types such as audio, lyrics, and metadata into our unified system. Music recommendation is essential in today's streaming platforms. However, most current systems struggle with key challenges like personalization, diversity, novelty, and contextual relevance. Traditional methods rely heavily on collaborative filtering or handcrafted features, which often fall short in capturing the full richness of musical content. The goal is to improve similarity modeling by leveraging deep learning, specifically transformer architectures, on multimodal music data. The objectives of this work are threefold. First, I aim to analyze how transformers can improve similarity detection across modalities. Second, evaluate the integration of music ontologies into neural systems to guide semantic relationships. And third, assess how this combined approach can be used to build better personalized recommendation systems. Neural system architecture. Each modality, audio, lyrics, and metadata is first processed independently using specialized transformer models. Features are extracted from each stream, then aligned and fused into multimodal embedded space. The ontology component provides additional semantic context to guide similarity judgments and improve interpretability. Another important aspect is the ontology-driven approach. I manually constructed an OL-based ontology with entities such as song, artist, genre, and their relationships. These symbolic structures are encoded into embeddings and integrated into the transformer model. During inference, the ontology layer improves context awarenesses, enabling filtering and disambiguation. This is especially helpful when metadata is sparse or ambiguous. I've used and fine-tuned several pre-trained models for this study: Wave2Vec for audio, AST for spectrograms, Clap and Mullen for multimodal tasks. These models were fine-tuned on music datasets to better capture domain-specific patterns. This fine-tuning also helps with the cold start problem by enabling the model to infer similarities from content, even in the absence of interaction history. For the evaluation, I've used four datasets: Million-Son dataset, GTZAN, Freesound 50K, and Free Music Archive. These datasets were chosen to ensure genre balance, metadata richness, and real-world diversity. Some datasets contain only the features or tags, while others provide raw data, allowing us to test various combinations of modalities. Data preparation. Audio samples were trimmed to 10 to 30 seconds to capture sufficient musical structure while maintaining computational efficiency. A 22.05 kHz sampling rate was used, balancing fidelity and training costs. Ethical considerations were also central in data selection, and I prioritized open licensed datasets to ensure legal reproducibility. Here are some training settings for each model: batch sizes, learning rates, etc. And dropout and learning rate schedulers were applied for generalization and stability. Pitch shifting and noise injection improved robustness, especially in audio-only models. I've used standard information retrieval metrics. Precision and recall measure how relevant the recommendations are. F1 score balances these two. mentioned, mean average precision evaluates ranking performance. Mappa 10 was used to specifically assess the top 10 recommendations, which is most relevant in streaming contexts. Results and analysis. Evaluated standalone and hybrid models. AST performed best among audio-only models due to its spectrogram focus. The hybrid model, combining Web2Vec, AST, and BERT, significantly outperformed others. It efficiently integrates temporal, spectral, and semantic information for deeper similarity understanding. Compared to MuLAN, the hybrid transformer setup achieved better performance across all metrics. Integrating the ontology improved accuracy, novelty, and diversity. Semantic descriptors help disambiguate similar tracks and promoted underrepresented genres. The ontology also provided interpretability by offering traceable relationships. Example, why a song was recommended. Evaluation metrics were even linked into the ontology to model feedback loops in system improvement. A major concern is computational cost. Transformer models require large memory and GPU, which can introduce issues in deployments. However, several strategies might help to mitigate this. For example, using smaller transformers like Distilbert, involving pre-computing embeddings, or approximate noise net research. With this, integration into commercial platforms becomes feasible, particularly in hybrid cloud environments. For further work, it'd be good to consider integrating user interaction data, for example, liked playlists or skipping rates. Another thing would be good to explore early fusion techniques and expanding ontologies through automated knowledge graph generation. These steps will help personalize and scale the system further. To conclude, this study demonstrates how transformer-based models, especially when fused with audio and text and metadata and incorporated into ontologies, can significantly enhance music similarity analysis and recommendation. Contributions include a novel multimodal fusion strategy, integration of ontologies for semantic grounding, and fine-tune transformer models for cold start handling. This research takes a step toward more intelligent, inclusive, and context-aware music recommendation systems. Thank you, and I welcome your questions.